A dot B is a scalar. If I take the time derivative of A dot B, then I apply the chain rule, that is dA dt dot B plus A dot dB dt. This is a scalar. A cross B is a vector. The time derivative of the cross product of A and B, again I apply the chain rule, would be dA dt crossed with B plus A crossed with dB dt. I can give you an example of a cross product and take the time derivative. The angular momentum relative to point Q of a moving object. Here is point Q, and here is an object with mass m that is moving with velocity v. Mass m, and this is the position vector r of q. L of q, the angular momentum relative to point q, is defined as the position vector relative to point q cross p. Notice that this vector is very different if you choose different points of q. But I'm not going to address that issue now. You will see that somewhere else in this course. P equals mv. That's an intrinsic property of the motion of an object. Angular momentum is not. Angular momentum depends on where I choose my point q. Now I take dl q dt, which now, according to my chain rule, equals drq dt crossed with p plus rq relative to q cross times dp dt. Now we see something very interesting. For one thing, dp dt is force. dr dt is the velocity of that object m. But p equals mv. So the cross product between the vector v and mv must always be 0, because they are in the same direction. Theta is 0, and so the sine of theta is 0. So what we end up with is an extremely famous equation that the time derivative of angular momentum equals r cross f relative to point q, r relative to point q cross f. And that is the definition of the torque tau relative to point q. And this is a very, very important equation. We're going to see this many times in Newtonian mechanics, and this is not an easy concept to apply it properly. Change of angular momentum and torques, believe me, is one of the most difficult subjects in Newtonian mechanics.